For this lesson, you're going to think I have completely lost my mind, and what on earth does this have to do with Taylor polynomials and Lagrange error bound? And remember, I said the first couple of lessons are going to follow along quite nicely, and then we're going to depart that information completely. But by the end of our series work, when we learn all this information, we will loop back around and Taylor polynomials and Lagrange error bound will show up again. But for the next many lessons, we're going to depart it completely and start talking about today's sequences, and then next we'll start talking about just general series. So let's talk about what a sequence is. A sequence can be thought of as a list of numbers written in a definite order. Most of the elements of the sequence have a relationship. An infinite sequence has infinitely many terms in it. That's what the comma ... means. We usually define a sequence by talking about its nth term. This would be the nth term of the sequence. And the nth term generally defines the mathematical relationship between all of the elements, and that's what these are. There's the first term in the sequence, there's the second term, the third term, and all of those terms have a relationship that's usually defined by what's happening in the nth term. We visualize the sequence by plotting its terms on a number line. Here's just a real number line. We could even say this was the x-axis if we wanted to. And here would be the first term in the sequence, 1/2. There's the next term, the next term, the next term, and so on, all the way down to the nth term. And so that's how we define a sequence. So here's the nth term of a sequence. A sub n equals 3 plus -1 to the n. And it asks us to write the first 4 terms of this sequence. Well, there are some things we need to know. A sub n, being the nth term, defines each element in the sequence, and some things that aren't obvious is the starting point. Starting at n equal 1, unless you are told otherwise. If there's no defining, a sub n equals this for n greater than or equal to 2, or for n greater than or equal to 0, if you're not given any additional information, like we're not here, we are to assume that we start generating the elements of the sequence at a sub 1. So being given that a sub n is 3 plus -1 raised to the power of n, we'll generate the first 4 terms of the sequence, and this is how we would show them. This is where n equals 1. Here is where n equals 2, and so forth. So that says everywhere that a sub n has an n, here I'm going to write a 1. Here, I'm going to write a 2. Here, I'm going to write a 3. And that's how we generate the terms of a sequence. Again, starting at n equal 1, unless we're told otherwise, that's how we would generate the terms. So this winds up being 3 minus 1, because -1 raised to the power of an odd power is going to give us -1. So the first term in the sequence is 2. Here is 3 plus 1. The next term in the sequence is 4. Here is again 3 minus 1. That has a value of 2. Here is 3 plus 1. That has a value of 4. So the first 4 terms in the sequence are 2, 4, 2, 4. If this is a finite sequence, then we would just close our braces there. If it's an infinite sequence, we would show comma ... to let us know that n keeps tending toward infinity. So we can clearly see n is an integer, and there's the symbol for integers. And most importantly, n is always a positive integer. And we always start with n equal 1 unless we're told otherwise. So if we're given the nth term, then it's fairly easy to generate the sequence. Sometimes we're given some terms in the sequence and we're asked to find the nth term. Now, I'll be really honest with you, this doesn't happen a lot. This is just fundamental elementary sequence work here, but I want you to see that you could find the nth term if you were asked to. And it's based on the fact that we know, unless we're told otherwise, the first term is generated when n equals 1. The second one is generated when n equals 2, and so forth. So what we want to do is we want to find the nth term of a sequence that is 1/2. The relationship between 1/2 and 1/4 is, it could be written like so. 1/8 can be written like so. 1/16 can be written like so. And since we know that the first term comes from n equal 1, the second term from n equal 2, and so forth, then it's really easy to find the nth term. That would be 1/2 to the n. So there's the nth term for this sequence. And so that's one of the main ways that we'll find the nth term. When we have the first term that equals 1, sometimes it's easier to look at all the rest of the terms because lots of things have the result of 1, and it's not easy to see what manipulation was done using n to get 1 as the answer. So we still know that for this first one, that's where n equaled 1. Here is where n equaled 2, and so forth. So let's ask ourselves, for the nth term here, what was done on n to get us a result of 4? And our denominators are the only ones that are different. All of our numerators are the same. So we would ask, what could be done there to give us 4? That could be the same operation here, where n is 3, that would give us the result of 1/9. Hopefully you recognize perfect squares. So that's a perfect square. So if n equals 2, then 1/n squared would give us 4. If n equals 3, 1/n squared would give us 1/9. If n was 4, 1/n squared would give us 1/16. And you can see that in terms of n, that would be our nth term. We're, again, not asked to do this often on the actual AP, but I think it's good practice for you to see the relationship between where the elements in the sequence come from, how they're generated, and how we write that as the nth term. Products of consecutive positive integers occur quite often in sequences. We are going to see factorials a lot. Up until this point, we have seen factorials in building our polynomials, so we're quite aware of what those factorials look like, what they involve. The one thing that I haven't really pointed out up to this point, if you find yourself with 0 factorial, it is in fact true that 0 factorial has a value of 1. 0 factorial is not 0 times 0. I'm not going to cover the mathematics behind this. You're welcome to Google that if you want to, but what I would like for you to do is just take it on faith that anytime you encounter 0 factorial, it does indeed have a value of 1. On your calculator, there is a factorial that you can pull up on your calculator. So for instance, if you need 13 factorial or 11 factorial, instead of trying to do that by hand, hit your math button, and you're going to have in that screen, there'll be 4 things listed up here. One of those things is probability, PRB. It's the last thing over here. So hit your right arrow until you highlight probability, and then hit enter, and there'll be a list of, things under probability, and under number 4 it just shows an exclamation point, and that means factorial. So your calculator is going to be helpful if you need to find a value that involves a factorial that's higher than the ones that we know. So just kind of put that in your notes so you can refer back to it. All right, write the first 4 terms of the sequence. A sub n equals 2 to the n over the quantity n minus 1 factorial. So let's do that. A sub n equals 2 to the n over n minus 1 factorial. We want the first 4 terms of the sequence. We are not told to start anywhere, so we know we are going to start with n equal 1. So in this term, everywhere there is an n, I'm writing 1. In this term, everywhere there is an n, I'm writing 2. In this term, I'm replacing n with 3. And finally, in this term, I'm replacing n with 4. So this is 2 over 0 factorial, which as we just learned is 2 over 1. So the first element, the first term in the sequence is 2. This is 4 over 1 factorial. 1 factorial is also 1. This is 8 over 2 factorial, or 8 over 4, which is 2. This is 16 over 3 factorial. 3 factorial is 6. So this is 8 thirds. So there are the first 4 terms of this sequence, A sub n. Now, we'll get to why we care about sequences and what sequences are going to mean to us when we talk about convergence. There's our old friend convergence. We did that convergence and divergence idea when we talked about our improper integrals. And it turns out that we're really interested if our sequences converge or diverge. So let's see what it means for a sequence to converge. So for a sequence to be convergent, or for us to say it converges to a value of L, means first that the values of the sequence over time, or as n gets larger and larger, then the elements of the sequence should get closer to a value of L. But they must remain close. So for instance here, we have A sub n. For n equal 1, there's A sub 1, there's A sub 2, A sub 3, and so forth. As n gets larger and larger and larger and larger, and we'll call this a value of L, doesn't necessarily have to be 1, it could be any value, we see that as n tends toward infinity, the elements, if we put them in the plane, in the xy plane, or the n A sub n plane, where n is the inputs and the elements are the outputs, we see that these are getting, A sub n as n tends toward infinity, they're heading closer and closer and closer to a single value. And as n gets really large, as n gets really large, if the elements or members or terms in the sequence stay close to L, then we say A sub n, our sequence, converges, and converges specifically to L.